Hello everyone. Before diving into today's topic, we want to take a moment to thank you for your support. Every like, comment, and subscription truly makes a difference and helps this channel grow. If you enjoy our content and don't want to miss the next videos, subscribe to the channel and activate the notification bell to receive all updates. In the invisible heart of the space that surrounds us, every second a silent storm brushes past. A perpetual dance of particles from the sun that challenge the fragile, unseen barrier that protects us, Earth's magnetosphere. For millions of years, this impalpable shield has safeguarded life, deflecting deadly radiation and preventing our planet from slowly being stripped of its atmosphere, as happened to Mars. But what we know about this interaction, this silent clash between the solar wind and Earth, is still surprisingly incomplete. This is where SMILE comes in, the Solar Wind Magnetosphere Ionosphere Link Explorer. SMILE is not just another space probe. It is the result of an ambitious joint project between the European Space Agency, ESA, and the Chinese Academy of Sciences, CAS, an international collaboration that underscores how crucial it is today to understand the space environment around us. Its goal? To observe, for the first time, the dynamics that govern the connection between the solar wind, the magnetosphere, and the Earth's ionosphere, with unprecedented precision. In the vacuum of space, the solar wind behaves like an invisible river of charged particles, continuously emitted by the sun's corona. When this stream encounters Earth's magnetic field, it forms a complex structure, resembling a gigantic bubble, the magnetosphere. It is not a static barrier, but a dynamic, deformable region, constantly fluctuating due to variations in the solar wind. At times, this interaction can trigger violent events such as geomagnetic storms, capable of producing spectacular auroras, but also disabling satellites, interfering with radio communications, and damaging power grids on Earth. Until now, these interactions have been studied through scattered, partial observations made by satellites analyzing one point at a time. SMILE promises a radical shift. It will be able to obtain a global view of the magnetosphere, observing it, from the outside, through two complementary channels, ultraviolet light and X-rays. The true technological revolution of SMILE is called SXI, the Soft X-ray Imager. For the first time, X-rays will be used to directly observe the front line, where the solar wind meets the magnetosphere. A region called the bow shock, the shock wave that forms in front of Earth, like the bow of a ship cutting through water. When ions from the solar wind collide with neutral atoms in the outermost part of Earth's atmosphere, they produce X-ray emissions that SMILE will detect. It's like seeing, in real time, the footprints left by charged particles as they interact with our atmosphere. In addition, SMILE will be equipped with the UV imager, capable of mapping polar auroras in ultraviolet, and two instruments to directly measure the particle flow in surrounding space. By combining all these observations, scientists will be able to build a dynamic, three-dimensional model of the Sun-Earth interaction. A sort of living, pulsating map of the invisible forces that shape our space environment. But SMILE's importance goes far beyond pure science. We live in an age where our dependence on space technology is absolute. Communications, GPS, weather forecasting, defense, finance. All these sectors rely on orbiting infrastructures vulnerable to the effects of solar storms. Understanding how a geomagnetic disturbance forms, evolves, and especially how to predict it hours or days in advance, can make the difference between normalcy and chaos. In this sense, SMILE contributes to the growing field of space weather forecasting, which aims to become in the coming decades as routine a service as today's atmospheric weather forecasting. It's no coincidence that SMILE's orbital trajectory has been designed with extreme precision. The probe will follow a very wide elliptical orbit, taking it up to 121,000 kilometers from Earth, far beyond the magnetopause, the outer boundary of the magnetosphere. From this privileged position, it will be able to observe the entire structure of the magnetosphere and how it changes in response to solar wind impulses. And here, the space for fascinating speculation opens. While today we study the magnetosphere to protect our technology, tomorrow we might have to consider it a vital requirement for colonizing other planets. Mars, for instance, lost most of its atmosphere precisely because it lacks a global magnetic field. If one day we want to terraform other worlds, or live in environments without natural protection, we'll have to find a way to replicate, or simulate, a magnetosphere. In this light, SMILE is not just studying Earth. It's providing a key to understanding what the minimum requirements for life in extraterrestrial environments might be. No other satellite has ever attempted to capture the shape of the magnetosphere through X-ray imaging. SMILE will be the first to make the invisible visible, to reveal the secret dance between the Sun and Earth as a luminous, ever-changing choreography. The expected images are destined to become iconic: UV auroras flickering in real time, plasma structures warping under solar wind pressure, weaves of energy and matter chasing one another through the void. And yet, all of this is only the beginning. Because if SMILE succeeds in its mission, we will not only gain access to a new cartography of near-Earth space, but we will also lay the foundations for an entirely new branch of operational astrophysics. Until now, observation of the Sun-Earth system has been limited to a localized approach. Point data gathered by a handful of probes, combined with complex and often approximate simulations. With SMILE, the paradigm changes. Its success will pave the way for a new generation of missions that won't just observe individual phenomena but will understand their global evolution, as if watching a storm form from above. Imagine seeing in real time a coronal mass ejection, a gigantic cloud of plasma detaching from the Sun, cross the solar system and hit Earth. Imagine predicting precisely when its particles will cross the magnetopause, where induced currents will concentrate, and which satellites will be most at risk. SMILE will be the first step toward this synoptic vision of near space, a true three-dimensional space weather forecast. But this is not only a technological endeavor. SMILE is also a political, cultural, and symbolic probe. It is the first large-scale space mission jointly developed by Europe and China. In an age where international tensions make even joint declarations difficult, SMILE represents a rare example of scientific cooperation that transcends geopolitical boundaries. A mission that blends European engineering with Chinese science, Western design with Eastern production, shared dreams in the vastness of the cosmos. In this sense, SMILE studies not only the relationship between the Sun and the Earth, but also the one between human civilizations and their shared future in space. And challenges abound. X-ray imaging technology in space is still young. SMILE will face issues of calibration, radiation exposure, orbital stability, and real-time data synchronization. The volume of information it will gather will be immense and will require new analysis techniques, advanced machine learning, and networks of scientists around the world. But this very complexity is its greatest value. Every obstacle SMILE overcomes will be a step forward for all future missions. On a speculative level, the data SMILE provides could have even deeper implications. Some theoretical physicists suggest that the dynamics of the magnetosphere are not just a matter of electromagnetic interactions but may offer clues about the structure of the quantum field that permeates space. The boundary zone between the magnetosphere and the interplanetary medium is a place of turbulence, discontinuities, magnetic reconnections, phenomena that, on certain scales, could be analogous to those occurring on much larger cosmological scales. SMILE, although not designed with these objectives, could provide crucial data even for extreme hypotheses, such as analyzing broken symmetries of the electromagnetic field or indirectly verifying macroscopic quantum effects in plasma environments. Meanwhile, auroras will continue to dance across the northern and southern skies, captivating casual observers and die-hard astrophiles alike. But from now on, every time we see them, we'll know a little more. We'll know that behind those veils of light lies a network of cosmic forces, a subtle yet powerful bond between our star and our planet. A bond we can now finally observe in full, thanks to a silent satellite watching over us from afar. And as SMILE completes its wide orbits beyond the magnetopause, it reminds us that science is never an end in itself. It is the lens through which we decipher the invisible, the compass that guides us through unknown territories, the universal language that unites us under a sky with no borders. In space, as in knowledge, the most fascinating frontier is always the one we have yet to see. But with SMILE, we've taken a bold step toward that vision, a step that speaks of future, of cooperation, and of that tireless, wondrous curiosity that has always driven us to look beyond.